Okay, thank you for kind introduction, Andrea. Thank you. So I'm very glad to be here. So thank you for organizing this very excellent workshop. I already had a really nice experience. I'm really inspired with the many of the excellent talks. I want to do the similar thing to you, but I'm not sure I can do that. Then I'm a bit, I'll say, maybe not so familiar with many of the audience. I'm coming from the people with less, how they know each other. Then, but I hope you enjoy my talk. Okay, so let me first acknowledge. Let me thank to my great collaborators and co-workers and laboratory student members. Then here is it's a group member, group photo. It's about 20 person is working in the laboratory. Then also I have a lot of the excellent collaborators. Here Sato-san already gave a talk, and Kishen-san here in the Japanese traditional wear. Then also them other people with here, and Yoshi. With this when we host Yoshi and Long come to the Japan, we host something like here. Then okay, then we made some kind of the consortium named the Quantum Research Center for Chirality. Then this is a logo of the consortium. Now let me explain the meaning of the logo a little bit. Then here, this is a logo, okay? Then this means something chiral, okay? The meaning of the chiral. Okay, so we have a point here. Then we look at carefully, closely, so zooming. Okay, but actually it's very hard to see something chiral in a point. But let us open. Then chirality is a kind of the internal degree of freedom. Okay, in this case we use some 3 vectors to show the chirality. It's in this case, for example, it's R dot L cross S, something like that. Then actually, so to express such a physical quantity, the multiple description is really nice, as Professor Spalding gave a talk in the first day. So we have a lot of the, then in that case, electric toroidal multipole could be a candidate, is a really nice quantity to describe the chirality. Then that has a monopole, dipole, quadrupole. So there's a many higher order of the multipole, which is really nice to describe the chirality. Okay. Then, okay, if you have interest, please see this literature. Okay. Then, okay. So let us consider the meaning of such a chiral term. Simplest case is how to say coupling of the axial vector and the polar vector. Okay, here's some example. K, P dot L, K dot L, P. S is a spin, L is angular momentum, P is a momentum, K is a wave vector. Such a coupling gives a chiral term. Okay, work as a chiral term. Then let us apply this term to the vibration, atomic vibration. Then that's a really main topic of this workshop. Okay, so this is a slide illustration from the Sato-san's group paper. Then how say you can see the vibration of the atom. The important thing is how say when we see the in-plane dynamics, some atom shows a circular motion. Then another important thing is they how say when we see the different location within the unit cell, they have a phase difference. That's why they obtained a wave number. Then at the same time, they show the circular motion. So you can understand the meaning of this, in this case, maybe K dot L. Okay? So K dot L is a really nice value to explain the essence of the chiral phonon. Okay, then let us make a similar consideration for the electric system. In this case, we have a helix in front of the mirror. Then behind, we have another helix with the opposite handedness. Okay, then let us drive the electron from the top to the bottom. Okay, then if we have suppose we have this term with regard to spin. Okay, now when we drive electron, it has a momentum that will lock the spin direction. This is what I'm writing here, illustrating here. So when electron drops, that locks the spin direction, in this case downward. But behind the mirror, the physical situation becomes the total opposite. Of course, electron can flow from the top to the bottom, but the important thing is the spin direction becomes opposite. That's what maybe you can say that's a famous spin momentum locking scenario. But actually, it shows such a really nice, intuitive picture and the kind of material regardless. So they could be organic material and also inorganic crystals. Okay, as Long and Yoshi already showed the really excellent data about the cis, they're mostly working on the molecules. Okay, the many kinds of molecule, they all show the cis data. That's amazing. Then in my case, I'm working on this side. I like a macroscopic scale. Okay, then I have several crystals, then try to see what kind of cis response will appear in these materials. So let me explain the more detail of these crystals. One is a chalcogranite, but in this case, we intercalate the chromium atom. Okay, mother compound is a niobium sulfide. Then other candidate is a disilicide. Okay, and then another one is a really famous crystal quartz. Then physical properties are slightly different depending on the material. First two is a metallic material, but quartz, of course, it's an insulator. More precisely, it's a dielectric material. As for the magnetic property, the first material shows the helimagnetic phase transition. This is a famous material, famous for some emerging of the chiral spin texture in this compound below the transition temperature. But at room temperature, its phase transition temperature is about 130 Kelvin. Now, so at room temperature, it shows paramagnetism. Okay, then in the second case, that it shows a diamagnetic property. So the electric structure is totally different from this and that guys. Then quartz also is famous for its diamagnetic property. Okay, so we have this kind of material. Then another problem is how to detect spin angular momentum, spin polarization in the material. It's a really tough work. Okay, so in the first experiment I demonstrated, he used the mode detector, but it's only available for the photo emission electrons, emitted electrons. It's very hard to apply it to the solid state device. Then another type, there are many variants. So maybe we can use the optical probe or some tunneling spectroscopy, magnetoresistance, or some anomalous Hall effect, resonance. So now we have several methods, many methods to probe the spin polarization in the material. Then in my case, we focus on this method. So let me explain the detail. Maybe you are really familiar with some spin Hall effect, but just in case, let me explain how the device would work. So here we have a chiral material. Then we put the electrode on the top of the crystal. Then let us apply current to the chiral crystal, which makes polarized spins. But it's assumption. Okay, if such assumption is valid, what we can expect, because of the large difference of the spin population, some spin can be absorbed toward the electrode. Then once we have a spin, such a spin current, spin diffusive current, it can be converted into a charge current because of the inverse spin Hall effect. Then eventually we can detect, we can have a transverse voltage. Okay? If our assumption is valid, this device would work as we expected. Okay? So the point is we can do the whole kind of whole measurement without applying magnetic field. That's the point. Okay, the advantage of this device, we can even examine the inverse effect of cis. So when we apply the current to this transverse electrode, that can induce a spin into the chiral material. Okay, once chiral material receives the spin polarization, it should show the voltage as to satisfy the reciprocal relationship of the cis. So in the second case, if we have a signal, we can demonstrate the non-reciprocal relationship of the cis phenomena. Okay, that's what we expect when we have an idea to make this kind of the device. Then eventually it turns out this method is really useful to detect the spin polarization in chiral materials. Okay, then let me go into the detail. So here the example of the device. In this case, we make a micrometer size sample using the fabrication technique. Then we put the electrode. So at the center, we put the tungsten. It's good for the spin Hall, inverse spin Hall effect detection because it has a really large spin Hall angle. Then we also put the several electrodes. Okay, so if we apply current throughout the sample, then if we measure the whole, if we get the whole voltage, that's evidence of the cis effect. Okay, when we can examine the inverse response. Okay, when we apply the current to the electrode, then if we have a longitudinal voltage, that means the inverse cis effect valid. If we can apply a part of the sample, okay, if in that case, then if we have a signal in some kind of a non-local configuration, if it's true, maybe signal should reflect the handedness of crystal, so we can prove the handedness of the material. We can do the locational dependent handedness detection. Okay. So let me show the data. This is the first data. When I saw this data, I'm really surprised. The point is the whole voltage appeared at room temperature without magnetic field. And another thing is the magnitude, the vertical axis, the signal magnitude is really large. Okay, so in the order of the millivolt appears for the against the milliampere current applications. So really huge. Then actually, so we made 3 devices, but unfortunately or unfortunately, I don't know. We didn't know the meaning of this data, but we made data. So we have this kind of data. Then fortunately now, we have another type of the transport measurement which enable us the chirality determination. That is called the electromagnetic-chiral anisotropy effect. Okay? When we apply the current magnetic field along the direction of the current, which modulates the magnitude of the resistance, then actually this sign, okay, is depending on the handedness of crystal. Then we performed this kind of the transport measurement. Then these three devices show the different sign of the slope. Then this slope a coincident shows a really good agreement in terms of the sign of the slope. So we're convinced that this data is coming from the something kernel. So that's why we believe this data. So we can say this data is a cis response found in the chiral inorganic crystal. Then let us check the non-reciprocal relationship. This is the inverse effect. Again, we apply the current to the electrode. Then even in this case, we have a longitudinal signal. Okay, the sign of the signal coincides with a direct effect. Then magnitude is almost the same. So it's a really reciprocal relationship is hold the cis phenomena. Okay, then let me just say something about the physical property, electric structure of this compound. This compound shows has a magnetic transition at low temperature, okay, magnetic order at low temperature, which means this guy has a localized electron as well as the conduction electrons. Okay, maybe partly because of such electric structure, we have a large enhancement of the cis signal. Actually, we perform the similar experiment by using another type of the chiral crystal. It does not show any magnetic order at lowest temperature. So its structure is a dielectric. They show the diamagnetism. Okay, so which means only this material has only itinerant electron spins. Okay, in this case, we have a similar cis signal, whole signal, but the magnitude of signal is about 1,000 times smaller than the previous case. Okay, we don't know why, but definitely the electric structure is different between these two materials. Then another interesting thing, just let us check the locational dependence of the cis signal. So here let us apply the current is just the left part of the sample, or right part of the sample, or just center part of the sample. Even in that cases, we can have a signal. Then again, we can evaluate the handedness of each location by using the electromagnetic chiral effect. Then it turned out this crystal is not homogeneous in terms of the chirality, crystal chirality. So it's a chiral, it has a chiral grain and this structure. So this locational data, demonstrate the chirality mapping in these micrometer size samples. Okay. Then also let me stress the surprising aspect of this device. So that's the distance separation between the electrode and the location for current injection. So here's a length scale. So it's about 10 micrometers away from the current injection places. So actually, in the first generation, such a gap is about 1 micrometer. Then in the second generation, gap is about 10 micrometer. In third generation, we do same experiment in a millimeter sample. Even in this case, we can have a non-local signal. This is really amazing. Of course, it's really beyond our conventional understanding of spin diffusion length. So here you can see the typical value of the spin diffusion length. So apparently this chiral crystal can, can transport really over long distance or through the crystals. Then of course, but this is a crystal, so it definitely has an electric band structure. Then also it's a chiral crystal. That's why it has an anti-symmetric spin-orbit coupling, which splits as an electric band structure. We can have a spin-dependent electric structures, film surface. Then first idea to show the such a spin polarization phenomena would be the famous Rashba-Edelstein scenario. Okay, when we apply the current, it induces some shift of the mass of the film sphere that induces some spin polarization. But usually the effect is really tiny. To detect the Rashba-Edelstein effect is a really hard work. But in our case, I don't know why, but we easily detect the signal because the combustion rate is almost 1 ohm. Okay, so it's really amazing. The another thing, Rashba-Edelstein effect should occur within the region where current is injected. Why we can have a signal in such a distance location from the current injection? We don't know why, but we do the experiment at room temperature. So in between, we just have the material. So maybe it vibrates something, vibrate atoms. So now it's time to investigate the chiral phonons. Okay, then for the investigation of the chiral phonon, the insulative material is much nicer because they don't have any electrons for the transport. And the quartz shows a diamagnetic magnetic property, so which means a spinless and a no magnon contribution is expected. Then another good thing will be the band gap is very huge. So maybe there's no, thermally excited electron contributions. Another thing is, yes, or then, but what make, what kind of transport mechanism is expected for the quartz? One idea is we may induce a dielectric current to such an insulative material. Or if we use some optical excitation, we can induce a shift current. Or another candidate with just atomic vibration, so collective atomic vibration, known as chiral phonons. Then we bravely made a similar device against the quartz. Then actually, was in our first experiment, we have tried the spin injection from the top electrode, then the spin detection in the another electrode. Then we somehow have a signal. However, with a careful analysis, the signal is proportional to the input power of the first electrode. So it's related, so it seems that it's correlated to the thermal agitation. So that's why I asked the student in the very last occasion for his master graduation. It was, I remember, it's maybe December. His graduation is March. So please make a new device and make a measurement. Then we put the heater on the top of the quartz. Then the other side is connected to the heater bus. Then we induce the thermal flow. Then let us try to measure the spin Hall signal as we demonstrated for the chiral metallic materials. Then actually for the thermal experiments, there are many artifacts are involved. So that's why we decided to perform the experiment at cryogenic temperature to reduce the artifact from the heat convection or heat irradiation, something other. Okay, then this is the data. So here you can see the data as a function of the power or as a function of the temperature difference. We could have a signal in both electrodes. Okay, then if we change the handedness of quartz from the left to right, the sign of the signal becomes the opposite. Then also the data shows some temperature dependence. Okay, in the next panel, let me plot the slope intensity as a function of the temperature. So in the upper panel, show the quartz with a left-handed and right-handed quartz with a detection electrode of tungsten. Okay, it shows some kind of peak structure around 10 Kelvin. The important thing is, of course, the sign of the signal is opposite again to the against the handedness of quartz. Okay, then when we replace the detection electrode from tungsten to platinum, this relationship becomes totally opposite. In this case, left quartz shows a negative peak structure. For the right quartz, right-handed quartz shows a positive peak structure. Then another important issue. Let us put. We made also we measure the thermal conductivity of quartz. Then here we put the data. We put the data here. Then you can see the coincidence of the peak position, which means that our transport data strongly correlated with the thermal phenomena. Now here, just the Chiral Phonons can make a contribution to such a transport response. Then when we submit the paper to journal, referee kindly made a lot of requests of the control experiments. Then we did a lot of things. Then we also same experiment in the A-Chiral material, no signal here. We also investigate the anisotropy of the crystal direction. So it's a less really anisotropic phenomena. Then referee shows let us change the, you need to change the direction of heat flow. It's a very tough requirement. So we turn the crystal, then have the same signal. Then also this is spintronics knowledge, so we change the thickness of the tungsten electrode. It shows the apparent spin-dependent signal. Then finally, referee required magnetic field response. We do the experiment without a magnetic field, but he's very keen, he or she, I don't know, but very keen against a magnetic field response. Actually, if we apply the magnetic field, that would induce some additional effect, like a Neronski effect. Okay, we have if charge current, then apply magnetic field, that would induce additional additive Neronski effect. So that would be the artifact. Only I think this direction, magnetic field apply only when apply along the heat flow direction. Maybe we can have some meaningful data. So here we can slightly see some magnetic field dependence of the signal. I'm not sure how large it is, but maybe so yesterday, so Professor Li showed us, argued the possibility of the thermal Hall effect in quartz. Maybe I think this data is somehow related. It corresponds to the planar nice thermal Hall effect. Okay, anyway, we could have a really large signal. So what kind of, what Chiral phonon is working Hall? Because we have, really nice dispersion. Of course, the point is, dispersion shows some angular momentum dependence. Then for the acoustic branch, we have a really apparent clear split of the branches. Then we can calculate how large angular momentum can be carried by the Chiral phonon propagation by using the Boltzmann equation with some assumption of the parameter. So here is a calculation. We can see some kind of the angular momentum value which carried by the Chiral phonon. It shows some peak structure as a function of temperature. Also, the apparent there's a handedness dependence. Then this is exactly what we observe in the experiments. Okay, so Chiral phonon can induce a spin signal in a transverse direction. But the problem, how to understand the mechanism behind such a phenomenon. We have here the cross-section of this device. Then we have an electrode. We have a back crystal, which has a Chiral phonon propagate in the back part. But how we can convert the angular momentum here to there, and then from the atomic system to the electric system. It's a very big issue to understand. Okay. So this is a summary of what we observed in the SPICE phenomena. As Long demonstrated, it shows a really large spin polarization, particularly for the chiral molecules. Then we can see the very robust spin polarized state in any kind of material. Then also it shows a long-range nature. Okay, but there are many, many unsolved issues we should work on much harder to reveal the mystery of the SPICE. Okay, thank you for your kind attention.